Tautomerism is a concept of interchanging functional groups. For example, if you have a ketone, it can convert into an enol form. And it happens on its own, or it can be enhanced in acidic and basic medium. Okay. Here, basically, you are breaking C double bond O and CH bond, and here you are making OH and C double bond C. Okay. And overall energy which is required is 50 kilojoules approximately, which means the interchanging into one functional group to the other functional group is hardly driven by a small amount of energy difference. Now, by some means, if enol is becoming stable and it is overpowering this 50 kilojoules of energy, then reaction will start moving in the forward direction. So it is extremely equilibrium sensitive. So equilibrium can drive more on the right hand side or the left hand side, depending upon how much amount of stability factors you will have. Okay, clear?
Yes, sir.
Right. The stability of enol can be achieved by intramolecular hydrogen bonding or resonance or any form of aromaticity. For example, if you take this beta diketones, beta diketones will have a strong hydrogen bonding in this enol form. That's why it is driving more in the forward direction and making the enol content as 76%. Okay. Now, if you have only aldehyde on both sides, the enol percentage will be quite high. Okay.
Yes, sir.
Reason being, first, the hydrogen bonding will be strong here. And second, there is no disturbing groups like this. Like what happens here, the resonance is supposed to happen, but at the same time, there is a
Somewhere.
hyperconjugation which is trying to push it here. Okay.
Yes, sir.
Because of which the stability of this resonance would be slightly lesser. जितने ज्यादा donating groups, more the donating groups which you will have, less will be the enol content you will notice. That's why you will notice this has around 98 percentage, 84 percentage. If both methyls are there, this comes to around 76 percentage. By the time you come towards ester, right? If it is called as beta keto ester, this is beta keto ester, then the percentage enol is hardly observed. It is only 8.3 percentage. If it is beta diesters, it is almost 0 percentage. And if you have both sides phenyls, right? Phenyls will give you an extended conjugation. It will give an extended conjugation. That means even though you have pi bond here like this, for example, if at all I draw it here, for instance, if you have O and H here with a double bond O making a hydrogen bond here, and then I have a phenyl group on this end like this, correct? And here is the enol form which you have, correct? This way, okay? Sorry, here also I have to write the ring form. So here, if at all I write the ring form, then what happens is this is the extension which you will notice. And due to this extension of the resonance, the stability is more observed. Clear, beta? Right.
Yes,
So
sir.
that's the reason why this will almost have 100 percentage of enol content. Due to aromaticity, you can judge CBA, aromaticity and regular resonance. In the case of bridgeheads, obviously here you cannot make any enol form because at the bridge positions you cannot make a double bond. Brett's rule, it is violating Brett's rule. Here you can make even more. So CBA. Ring effect, if you have a ring chain, usually ring chains will have a better double bond character than a straight chain. That's why ring will always have a better enol form. Okay. Steric group, if you have mesitylene groups on both ends, this big is the group here. Then obviously the bond angle, which is around 109 degrees in sp3 carbon, will have more repulsions compared to sp2 carbon. So it will like to be more in the enol form rather than keto form. Next, if you have this particular ketone, it would hardly have any percentage keto form because of the strong repulsions in their uh, in their conformation form. Between these two carbons, if you make a conformation, there is huge torsional repulsions here. Got it? But if you make it into an enol form, now it will have a strong hydrogen bonding. Okay. And on the same side, if you have this particular ketone, diketone, alpha diketone, they would always want to be in the anti-bond, anti-conformation. And that's why this rotation is completely restricted. And if the rotation is restricted, you cannot get into the enol form. Okay. That's why this will be almost 100%. Here, this will be almost 100%. Next thing what you need to know is the solvent effect, that if you have only gaseous phase, enol content is relatively more. In non-polar medium, enol content would be more. Liquid phase, the enol content starts decreasing. By the time it comes to aqueous solution, enol content is less. Because in aqueous solution, the hydrogen bond is does not dependent on intra-H. The hydrogen bond can be compensated from intermolecular hydrogen bonding as well. That's why in water it will be hardly any enol content observed. Okay,
Yes, sir.
right, next. And if you have 0% enol content cases, now these are all the cases where there are no enol form. Okay, next. Now, what is the mechanism that happens in tautomerism? See, this is an acid catalyzed mechanism where a lone pair from a double bond O connects here. So water would take H plus from here, pi bond will be pushed, you will get this enol form. And in base catalyzed mechanism, OH minus will be the first one to take, enolate ion will be forming. So this is an important area to understand, that in the acid catalyzed mechanism, there is no enolate ion. Directly an enol is formed. But in base catalyzed mechanism, first an enolate ion is formed and then it will take H plus to form an enol. That's the main difference which you will notice in the mechanisms going ahead. Okay. So this is a part you need to remember, what happens in acid catalyzed part and base catalyzed part. Clear, beta?
Yes, sir.
Now let us see the following reactions. First one is alpha racemization. I have an aldehyde or a keto group here, and adjacent to that at the alpha position there is a chiral center here. And let's say if I take a pure enantiomer and I take it in acidic medium or a basic medium, because they both go through this enol formation. So during the enol formation, you will get this carbon to become sp2. And due to that sp2 formation, now again when they form ketone, you can get 50% of one enantiomer, 50% of its mirror image enantiomer. Okay. So what happens, even if you take the pure form which is present at the alpha position, it would start getting into racemization. Clear? Now you can see this mechanism. From here in acidic medium, you will get water to be removed and enol is forming here. And that enol can take H plus either from the top of the orbital or from the bottom of the orbital. As it does, you will get a keto form, sorry, aldehyde form here with H on the top or H on the bottom. That makes it 50-50 percentage. Any doubt in alpha racemization? Please do check.
पर ये aldehyde हमेशा होगा एक ग्रुप, वो चार ग्रुप में से जो कार्य कर रहा है, तो सर हमेशा इधर रेसमाइजेशन होगा।
हाँ, जब तक वो अल्फा पोजीशन पे कायरल सेंटर है, हमेशा रेसिमाइजेशन होगा।
और aldehyde होगा तब।
नहीं, कीटोन भी होगा तो भी, यहाँ पर कीटोन होगा तो क्या फर्क पड़ रहा है, ये एच के बदले में आर है।
हाँ सर ठीक है सर, मतलब
ठीक है।
पर फर्क नहीं पड़ता ग्रुप्स कौन से होंगे दूसरे वाले,
नहीं
मतलब वो इनोल फॉर्म स्टेबल है कि नहीं, ऐसा कुछ।
नहीं नहीं नहीं, देखो, परसेंटेज यहाँ पर अज्यूम करके चल रहे हैं कि ये कीटोन में ही ज्यादा स्टेबल है, कीटोन या अल्डिहाइड में ज्यादा स्टेबल है, ये अज्यूम करके चल रहा है। इसके लिए हम लोग कोई इनॉल फॉर्म इसका लिख नहीं रहे ना। इनॉल फॉर्म को हम लोग एक इंटरमीडिएट की तरह देख रहे हैं कि
यस सर ठीक है।
इंटरमीडिएट फॉर्म करेगा फिर वापस वो आल्डिहाइड या कीटोन में आ जाएगा।
हाँ सर।
ठीक है।
सर पर अगर उसका इनोल फॉर्म स्टेबल है तो फिर वो उधर ही रुक जाएगा।
उधर रुकेगा नहीं बेटा, देखो इक्विलिब्रियम में ही रहेगा। तो
हाँ।
आप अभी कंटेंट की बात होगी ना, अगर कंटेंट की बात नहीं हो रही हम लोग की यहाँ पर, हम लोग कह रहे जो ऑल्डिहाइड था ओरिजिनली, अभी ऑल्डिहाइड कैसा रहेगा, चाहे वो 50% ही हो, 10% ही क्यों ना हो, दैट 10% विल बी रेसिमाइज्ड। ठीक है,
यस।
समझ गया। हो सकता है इनॉल ज्यादा परसेंटेज में हो इस केस में, सो 90% इनॉल वैसा का वैसा ही है। ठीक है, बट जो 10% कीटोन है वो रेसिमाइज्ड है। ओके,
हाँ सर।
नेक्स्ट, इफ बाई चांस देर आर two positions, alpha and beta position. You know that at beta position there is no tautomerism. So at alpha position only the S will convert into 50% of this S and 50% of R. And we cannot say exactly 50% anymore because these are not enantiomers. Correct? So what are they? They are pair of diastereomers. Is that clear?
यस सर।
Okay. So it might be happening like something could be 48 percentage and this could be 52 percentage. We don't know. We can't guarantee that, but definitely we can say that they will be pair of diastereomers. Okay, so this concept is called alpha racemization. See the second reaction. The second reaction is called alpha deuteration. Alpha deuteration is a case where you will have an aldehyde here, and if at all there is an alpha hydrogen, that alpha hydrogen is being replaced by deuterium. And while replacing, again it will go through the mechanism of a enol formation. You will get 50-50 percentage of the products. Okay, so it is kind of getting racemized, at the same time it is also getting converted into a deuteration. Okay,
यस।
so but for this to happen we require a prolonged time. It will not happen easily, it will happen a long time. So therefore what you would notice is that between these two you will have all the hydrogens being replaced at one point of time. Okay, see, here it is happening because it is showing a primary isotopic effect. Primary isotopic effect is judged on the basis of what is the rate ratio of hydrogen versus deuterium. And if at all the rate ratio is found somewhere between 2 to 8 or above, usually if it is more than 8 also or at least greater than 2, then we say it is primary isotopic effect. Okay, if it is secondary isotopic effect, we will hardly see that it is between 1 to 2. And most of the time, if we say there is a primary isotopic effect, that means we are referring to, sorry, when we say isotopic effect is present, that means we are referring to primary isotopic effect. Okay, and during the conversion, मतलब कीटोन से इनॉल में जब कन्वर्ट हो रहा है ना, उसका अगर रेट हम लोग कंपेयर करेंगे, अगर यहां पर ड्यूटेरियम होता और वो कन्वर्ट होता है इनॉल में, और हाइड्रोजन होता वो कन्वर्ट होता है इनॉल में, इफ यू कंपेयर दीज टू, its ratio would come somewhere in between these two parts, which suggests that this is a primary isotopic effect. And whenever there is a primary isotopic effect, at the positions where you get an anion or a double bond in the enol form, all of those positions hydrogens are replaced by deuterium. Okay, and you can notice in all these cases how many are getting replaced. Here you can see 3 and 3, 6 getting replaced, 2 and 2, 4 getting replaced, 2 and 2, 4 getting replaced, 3 and 2, 5 getting replaced, 1 and 3, 4 getting replaced. Here 0, there is no alpha uh, carbon only. Here it is 0. And when it comes to phenol, phenol is given in an enol form. So when you write again back to the enol form, how many are replaced? So you can write the enol form like this. If I can put here as this form, by which you can get this negative charge moving at these three positions, which means you can have all the deuteriums replaced here, and O minus can be present in a resonating form. So there also it can get replaced. So how many deuteriums are replaced? Four of them. And here it is zero because there is no alpha hydrogen, which is sp3 carbon. Now here if you notice, This is not alpha, but this is gamma. This is alpha, beta, and gamma. Tautomerism can be extended towards gamma, delta, epsilon, and so on, depending upon whether it can give resonance or not. So if at all I remove hydrogen from here, you'll get CH2 minus, and that can push double bond here, and you get a negative charge on this carbon. And thereafter that negative charge can go onto the oxygen as negative. So that means there is an extended resonance here. So wherever there is a negative charge coming, replace all those hydrogens with deuterium. So these three, here one, and that's it. This is the total four of the replacements which you will notice.
तो वो आय है सर, आय में भी ऐसा जैसे फिनॉल में किया था वैसे कुछ करके नहीं देख सकते क्या?
Pardon?
नथिंग नथिंग सर, सॉरी, समझा।
फिनॉल में तो फिनॉल ही ज्यादा स्टेबल है ना, अल्डिहाइड ज्यादा, इनॉल ज्यादा स्टेबल है, तो हम लोग इनॉल के बेसिस पे बता रहे
हाँ सर,
हैं।
समझा।
Right? Next few cases I have given, you can go through it once. Okay? There are multiple cases in the assignment also, you can just go through it once. Check out how many are getting replaced. Okay? Now, next one is about alpha halogenation. Okay? So this is the third reaction, which is alpha halogenation. Check out alpha halogenation. This can be done both by acid catalyzed mechanism or base catalyzed. First, let us start with acid catalyzed mechanism. For that, you take any halogen. Okay. Here, these halogens work the best as long it is chlorine, bromine, and iodine, not for fluorine. So, in that case, if you take it in acidic medium, how is the mechanism happening? Let's see. So, first in acidic medium, it will take H plus, correct? And thereafter, ACO minus will take H plus from here, pushing it into an enol form. So, you got an enol form. And formation of enol itself is a rate determining step here, very important to understand. Okay. Enol formation itself will take time here. So that is a rate determining step. Keep that in mind. Yes. Okay, beta. And next. Now the pi bond attacking on X, their X minus will be broken, which makes into CX bond. And as that happens, this carbon's positive charge will be resonance stabilized by oxygen. You will get into this form. Okay. And remove this H plus, you will get the uh, alpha getting substituted. And since this step is happening after the rate determining step, so it doesn't matter whether you do it for chlorination, bromination or iodination, the rate reaction will be same. The rate of the reaction will be same. Okay.
यस सर।
Now, notice this one. What if I give you excess of chlorine this time? Suppose हमने excess of chlorine दिया, क्या problem होगा? We know that first one chlorine will come, correct? Now here is the interesting part. After one chlorine has come here, if the acetate takes away H plus from here, correct? Acetate takes H plus from here, you would start getting negative charge here, isn't it? Correct? While पूरा negative charge नहीं आएगा, but you would notice that the negative charge can also make a d orbital resonance with chlorine, right? Isn't it? मतलब it could have been given this side also to make an enol form like this, or it could go on this side also, making kind of an d orbital resonance, isn't it?
हाँ।
Clear? Now, because chlorine is more withdrawing group here, chlorine is more withdrawing group here, this would try to make more of an d orbital resonance on this side, and this side it will be less observed. Moreover, if you notice in ACO minus here, if you remove this H plus and try to bring this H plus here, this is more acidic hydrogen than this one, isn't it? Because this carbon is connected with the hydrogen, correct? So this hydrogen is more acidic. So इस तरफ जाने का रास्ता वैसे भी कम होगा. And that is the reason why we saw that ये enol formation बहुत ही slow हो रहा था. Correct? And because of the chlorine present now the rate will become even much slower. So ऐसा नहीं कि यहाँ पे नहीं हो सकता है, but the chances of forming that will be very very less. Yes, clear है बेटा? Okay.
यस सर।
That's why even if you take excess na, You will not be seeing multiple number of halogens getting substituted in acidic medium. Clear?
हाँ सर सर
That's
वो
why
एसिडिक हाइड्रोजन से ऐसे कंपेयर किया हमने।
ये कार्बन हाइड्रोजन का बॉन्ड, ऑक्सीजन हाइड्रोजन का बॉन्ड, कौन सा ज्यादा एसिडिक है?
ओ सेकंड वाला।
सेकेंड वाला ना। तो कोई लेस एसिडिक ग्रुप क्या स्ट्रॉन्ग एसिडिक ग्रुप दे सकता है? नहीं ना।
अच्छा ठीक है सर हाँ।
ठीक है। So now notice this one. Here removing chlorine, here removing one, I mean one hydrogen with chlorine, that is possible. सिंगल टाइम हो सकता है, सेकेंड टाइम होना काफी मुश्किल है। ओके,
हाँ
clear? So if you take excess, one might come here, one might come here. That's it. That is the maximum you can expect. Here if you have this way and you take only one equivalent, more stable enol side आ सकता है. This side is a more stable enol. That side you will get chlorine forming. Correct? Does this make sense?
हाँ सर।
Right. Now notice this one. Suppose if I take 1 mole of aldehyde or a ketone and I take 1 mole of bromine, then the reaction would be more of equal amount. कि ये 1 mole होगा तो ये 1 mole कंज्यूम करेगा ताकि हमको 1 mole of alpha substitution मिले, 1 mole of HBr मिले. This is typically how the acid catalyze mechanism will take place. Now let us try to follow up on the base catalyze mechanism. Okay, check out. If you have OH minus, first what do we get? We'll get H plus away, and that will start forming enolate ion. Again, enolate ion will be the slow process here. Enolate ion form करने में भी time लगेगा. And then O minus will push here. Double bond will get a negative charge on this carbon. That will take X and leave behind this X here. So that way you can get X substituted here. Obviously, if it is a chiral center, you will have racemic form. And here also, since the addition of halogen is happening on the second step after the rate determining step, so the reactivity will be same for chlorine, bromine and iodine. Okay,
क्या सर क्या।
because this is a rate determining step बेटा, तो
हम्म,
इस केस में कोई हैलोजिनेशन तो नहीं हो रहा है.
हाँ हाँ ठीक
हैलोजिनेशन नेक्स्ट स्टेप्स में हो रहा है, तो उसका रेट सबके लिए सेम रहेगा. ओके,
है।
अब इस पॉइंट पे फिर से आते हैं, पहले मैकेनिज्म समझ के. ओके, मैं वो पॉइंट पे फिर से आता हूँ. पहले मैकेनिज्म समझते हैं. इफ एट ऑल यू हैव इन एक्सेस, व्हाट वुड हैपन? एक्सेस ब्रोमिनेशन या एक्सेस क्लोरिनेशन करेंगे तो क्या होगा? लेट अस अंडरस्टैंड. OH minus is removing H plus from here to get this enolate ion. ओके, क्या मैं ये बोल सकता हूं बिकॉज दिस इज अ रेट डिटरमाइनिंग स्टेप, ठीक है, इनोलेट आयन बनने का रेट डिटरमाइनिंग स्टेप है, तो इसका हाइड्रोजन का एसिडिक कैरेक्टर डिसाइड करेगा कि रेट फास्ट होगा या स्लो होगा, है ना? क्योंकि ये
हाँ
बेसिक मीडियम में मेन इंपॉर्टेंट काम यही होता है कि कार्ब एनियन बने, है ना? और कार्ब एनियन एक इंटरमीडिएट है. ओके, अब वो इंटरमीडिएट कितना फास्ट बन रहा है वो डिसाइड करेगा नेक्स्ट स्टेप फास्ट बनेगा कि नहीं. करेक्ट?
हाँ
इसके लिए यहां पर द एसिडिक नेचर ऑफ दिस कार्बन हाइड्रोजन बॉन्ड बिकम्स एक्सट्रीमली इंपॉर्टेंट बेसिक मीडियम में. मेक सेंस?
यस।
अभी क्या हो रहा है? सो फर्स्ट व्हेन यू टेक ब्रोमीन, एक ब्रोमीन तो सब्स्टिट्यूट हो गया, ठीक है, एक ब्रोमीन हो गया यहाँ पे सब्स्टिट्यूट. वन ब्रोमीन वंस इट कम्स ओवर हियर, अभी प्रॉब्लम क्या हो रहा है? दिस हाइड्रोजन इज बिकमिंग इवन मोर एसिडिक. मेक सेंस? Because bromine is a withdrawing group. Your carbon has a withdrawing group that makes that carbon hydrogen bond even more acidic. Okay. And because it is getting acidic, if the OH minus is being removed by this H plus, I mean, if it removes this H plus ion, the negative charge which it gets, it can go some d orbital resonance with bromine, but it can also form enolate ion because here there is nothing like a hydrogen which we have to compare here. Correct? इनॉल में जैसे कोई पहले हमने एसिडिक मीडियम में कंपैरिजन था, वैसा वो प्रॉब्लम नहीं है इधर. सो इन दैट केस नाउ द रेट may purely depends upon the acidic nature of this hydrogen. So stronger the acidic nature, quicker you can remove and more easily the enolate ion can form. And once an enolate ion forms, the pi bond can again attack on bromine, gets two bromine, get substituted. So what is it helping us to understand? That here in basic medium, the criteria mainly relies on whether you have more acidic hydrogen or not. Therefore, the rate only keeps increasing if you keep substituting more and more alpha halogens. Okay. सो हैलोजिनेशन तब तक होते रहेगा जब तक कि सारे अल्फा हाइड्रोजन्स कंज्यूम ना हो जाए. Yes, is this making sense? Because the main crux of this mechanism is only this point.
यस सर.
ठीक है. अब उसके बेसिस पे इस रिएक्शन पे वापस आ जाओ. Now notice this one. There are two alpha hydrogens, है ना? And I took 1 mole of bromine. So क्या होना चाहिए बेटा? पहला ब्रोमीन सब्स्टिट्यूट हुआ, ठीक है?
हाँ
क्या सेकेंड ब्रोमीन सब्स्टिट्यूट उसी जगह पे होगा या कोई नए मॉलिक्यूल पे होगा?
सर, उसी जगह पे होगा ना, और एक
उसी
बाकी
जगह
में.
पे होगा, बराबर. तो इसका मतलब है कि आप जब तक ये ब्रोमीन पूरा कंज्यूम एक ही मॉलिक्यूल के साथ नहीं होगा, तब तक वो दूसरे मॉलिक्यूल पे नहीं जाएगा ना.
हाँ सर.
इसके लिए इफ यू टेक 1 मोल एंड 1 मोल, तो इस ये ब्रोमीन पूरा का पूरा इसके हाफ मोल को कंज्यूम कर देगा पहले. हुँ?
यस.
ताकि दो ब्रोमीन्स वहीं पर आ जाए, है कि ना? राइट.
हाँ
सो इट इज लाइक, लेट्स से हमने 100 मॉलिक्यूल्स लिया, यहाँ पे 50 मॉलिक्यूल्स लिया, ठीक है. ये 50 मॉलिक्यूल्स यहाँ के 50 मॉलिक्यूल्स के साथ रिएक्ट करेंगे, ठीक है. और आपस में वो लोग क्या बना देंगे बेटा? those 50 molecules, these 50 molecules and these 50 molecules will try to make this product first. तो यहाँ पे 50 मॉलिक्यूल्स बच जाएंगे ना.
हाँ सर.
समझ गया ना? तो ये इंपॉर्टेंट पार्ट है कि यहाँ पे लिमिटिंग रिएजेंट कौन है? ब्रोमीन है. 1:1 रेशियो लोगे. पहले ऐसा नहीं था ना, एसिडिक मीडियम में दोनों इक्वल अमाउंट में हो रहा था.
हाँ.
बट यहाँ पे ऐसा नहीं होगा. यहाँ पे ब्रोमीन पूरा का पूरा कंज्यूम हो जाएगा. एक मॉलिक्यूल के साथ जितना कंज्यूम हो सकता है वो पूरा कंज्यूम हो जाएगा. उसके बाद ही फर्दर रिएक्शन हो सकता है. सो देयरफॉर यू विल गेट 0.5 ऑफ दिस वन एंड अनदर 0.5 ऑफ NaBr. ठीक है.
यस सर.
करेक्ट. लॉजिक क्लियर है?
हाँ सर.
बस अब यही लॉजिक लगाते हैं हम लोग एलोफॉर्म रिएक्शन में. ओके.
सर, एक ही मिनट रुक सकते हो क्या सर? एक ही मिनट.
यस यस. यू वांट टू गो थ्रू द क्वेश्चन?
नहीं सर, वॉशरूम जाके आता हूँ, एक ही मिनट.
ओके ओके. Right. So now let's apply this logic to haloform reaction. देखो, if you have an aldehyde like this or a ketone which has a methyl at the alpha position, that's compulsory. Methyl होना जरूरी है. If you
यस.
have methyl, then you react with bromine in the presence of NaOH, and I'm taking enough or sufficient amount of bromine. In that case, what is the product you will get? You will get HCO minus and CHBr3. This is called bromoform. The same reaction can be done with chloroform, bromine or iodine, which we call it as iodoform. Isn't it? रेट में कोई फर्क नहीं होगा because रेट सिर्फ और सिर्फ reactant पे डिपेंड करता है. Right? Now, as usual, when you take three bromines, all three bromines will be replaced first, right? And once all the bromines are being replaced, then and only then the remaining amount of OH minus will act like a nucleophile, attacks on this carbon. Pi bond will be replaced here, and you will get O minus, and O minus will push back because now it sees that CBr3 is a good leaving group. So CBr3 minus will come out. It will take H plus from the acid and precipitate, or separates itself as haloform. In this case, if it is bromine, it is bromoform.
सर,
Is this
फ्लोरीन के
making
साथ क्या
sense?
प्रॉब्लम हो रहा है सर?
फ्लोरीन F प्लस नहीं बन सकता है ना, बिकॉज these are all electrophilic substitution, right?
यस.
इसके लिए फ्लोरीन के साथ नहीं हो सकता है.
अच्छा ठीक है.
So now notice, if you have 1 mole is to 1 mole, obviously this 1 mole will consume all three hydrogens. So that means 1/3 of this is completely consumed. So only 2/3 moles are left here, right? And 1/3 of this is formed and 1/3 of this is formed. Correct?
हाँ सर.
And in the halogens, what you need to remember is that, it can be given in different formats. You can be given as chlorine in NaOH, or this one as a bleaching powder, CaOCl2. You can be given as KClO3 plus Cl minus in basic medium,
तो उसका मतलब क्या?
NaOCl. इसका मतलब सेम ही है, इसका मतलब ये Cl2 इन द प्रेजेंस ऑफ OH माइनस हो जाएगा।
अच्छा ठीक है।
NaOCl है, इसमें भी Cl प्लस आ जाएगा, NaOBr इसमें भी Br प्लस आ जाएगा, NaOI इसमें भी आयोडीन प्लस आ जाएगा, CaOI2 में भी आयोडीन प्लस आ जाएगा। सो ये these are different ways of representations, but all of them are giving X plus, which means they will get substituted at alpha position. Okay,
हाँ
now notice between, if you have this one in NaOH, now here is an interesting fact in the mechanism what we learned. The acidic hydrogen is an important criteria there, right? Now there is a hydrogen here, there is a hydrogen here. Which is more acidic hydrogen beta? This one.
हाँ, NO2 के
Correct.
बाद।
बराबर. So इसका मतलब iodines will get first substituted here, right? तो यहाँ पर substitution हो जाएंगे. And then the OH minus will attack because it notices that this is a good leaving group. So this group will come out and that will take H plus. So क्या हमको आइडोफॉर्म आ रहा है? नहीं आ रहा है. ठीक है. सो रिएक्शन तो हो रहा है लेकिन आइडोफॉर्म की तरफ नहीं आ रहा है. सो दैट मीन्स even though there is a open methyl group here, there is an open methyl group here, it is not necessary आइडोफॉर्म होना चाहिए.
फिर आयोडोफॉर्म मतलब CH(X3) के फॉर्म में कुछ तो बनना चाहिए क्या?
हाँ बेटा, येलो कलर प्रेसिपिटेट, CHI3 इज येलो कलर प्रेसिपिटेट. दैट इज अ क्राइटेरिया. ओके,
हाँ,
कि आइडोफॉर्म
थोड़ा।
रिएक्शन हो रहा है, इसका मतलब ये एक्सपेक्ट कि येलो कलर प्रेसिपिटेट बनना चाहिए.
अच्छा ठीक है।
If you have any electron withdrawing groups, these are all electron withdrawing groups. So if you have electron withdrawing groups, because this position is the one which will leave, that means you will never get iodoform in this case or haloform in this case. Okay. Now notice this case. Suppose if you have an active methylene group, this is an active methylene group, but both sides we should have either aldehyde or ketone. ये important criteria. Left hand side and right hand side we should only have aldehyde or ketone form.
तो
So in
एक
that
जगह
case,
एल्डिहाइड होता एक जगह कीटोन होता, तो फिर
that
एल्डिहाइड की
doesn't
तरफ
matter, doesn't
कौन?
matter. हाँ, तो aldehyde की तरफ रिएक्शन ज्यादा होता.
हाँ
ओके.
सर ठीक।
सो OH minus will attack here. ये बॉन्ड इधर चला जाएगा and after that it will break, right, giving you an acid and this CHI3. And now CI2 minus will take H plus from here, convert into this CHI2COH. And if you still have iodine and NaOH left, क्योंकि हम लोग excess में ही डाल रहे हैं I2 को, so in that case again the reaction will take place. So from here, this there is one more hydrogen which will be replaced via iodine, and then OH minus will attack. This time Ci3 might be relieved out, which will take H plus, and finally you will get haloform. Okay?
फिर एक्सेस I2 NaOH दिया होगा तो ही करना है कि
No,
खुद
no.
से भी करना
Usually नहीं देते ऐसे. आपको समझना है कि यहाँ पर एक्सेस है. ओके? ये
है?
सब रिएक्शंस में इतना भी स्ट्रिक्ट मत रहो. So if iodine and NaOH is given me, they are expecting you to understand कि आपको आइडोफॉर्म बनाना है.
राइट सर।
ठीक है बेटा. देखो. Here also, if you have I2 and NaOH, right, you can remove this part, isn't it? तो हो जाएगा आइडोफॉर्म. क्लियर?
हाँ सर
यहाँ
ठीक।
पर भी सेम, दोनों तरफ कीटोन है तो ये वाला एक्टिव हाइड्रोजन है, हो जाएगा आइडोफॉर्म.
हम्म।
अब ये नेक्स्ट वाला देखो बेटा, नेक्स्ट वाला केस इंपॉर्टेंट है. देखो यहाँ पर आयोडीन आयोडीन आ गया, बट द अदर साइड देयर इज एन एस्टर, isn't it? And since it is an ester, first OH minus will go attack here, you will get O minus, and after that this bond will be broken. When the bond is broken, you will get this as this C double bond O minus, and you will have this as CHI2 C double bond OR. Correct? Now
हाँ।
this cannot make any alpha substitute because यहाँ पे कोई tautomerism होगा ही नहीं. ये एस्टर है ना बेटा, एस्टर में tautomerism का नेचर बहुत ही वीक होता है.
हम्म।
Got it? Since
यस।
that does not happen, so reaction will end up here only. So furthermore reaction will not happen. So is the halogen happening? Is the haloform happening? No.
नो।
So what is the criteria you need to notice? एक्टिव मिथाइलिन के दोनों तरफ कार्बोनिल ग्रुप्स ही होने चाहिए, मतलब अल्डिहाइड या कीटोन्स या दोनों.
हाँ सर ठीक है।
ठीक है। नेक्स्ट, if you have alpha diketones, if you have methyl on either side, that will definitely give you iodoform. Okay, and since you will have this side and this side, both sides you can get iodoform. You can get two moles and you'll get an oxalate. If you have an acid here, then also nothing will happen. Here this will be COO minus, this will also become COO minus, and this group will give you CHI3. Okay, now even if you have a tert butyl on one side and methyl on one side, still there is noticeable amount of halo form. Although the reaction happens slower, you will still see CHI3 is forming. But if you have a phenyl groups on both sides, instead of tert butyl, now you have phenyl group, then the amount of iodoform notice is extremely low or negligible. So इस case में आप लोग you will assume it there is no reaction. Okay.
सर वैसे के ऊपर।
Okay. Basically, when the enol is forming here, correct? When the enol is forming here, you will not see much influence of this tertibutyl, while attacking of this group when OH minus is attacking, correct? But here when the phenyl is present here, correct? OH minus जब अटैक करेगा ऐसे, C डबल बॉन्ड O, CI3 है यहाँ पर ऐसे, let's say, okay, and OH minus is trying to attack here like this, isn't it? And you get this as O minus. Yeah. Now what happens? Instead of CI3 coming out, you will see phenyls can come out more easily because this is also a very stable carbanion. Correct? So this would become a better leaving group in that case if you have a phenyl. Yes, clear, beta. So that is why this is not noticeable amount of CHI3 निकलेगा नहीं from this case. Okay.
हाँ सर समझा।
Next one, we have this CH3 that will also become CHI3 here. Even if the alcohol is present, alcohol पहले oxidize हो जाएगा. After that, oxidize कैसे होता है ये हमने पहले learn किया है alcohol में. You remove H plus, you get O minus. O minus will take iodine here. You will get OI. OI becomes a good leaving, pulling group, which makes I minus to take H plus from here. Not I minus, OH minus, sorry. OH minus to take H plus from here. So you will get minus charge. Minus charge will push, iodine will come away. Again, you will get ketone. So once you get ketone, you will get a positive iodoform test. So you can see all of these will give positive iodoform test. Any doubt?
नो सर।
Haloform is clear?
हाँ सर।
Right. Now let's see alpha alkylation. Okay. Suppose if you have a keto group and I'm trying to use it with a base. Base will take H plus from this carbon, you will get CH2 minus. That will convert into an enolate ion. Okay. And enolate ion will make this carbon to become active with a delta negative charge. And that makes it as a good nucleophilic site to attack on Rx. And via SN2 mechanism, it would happen to give you this alpha substitution. Clear, beta?
हाँ सर।
But this becomes slightly different to understand if you have two different types of ketones. That means if you have an unsymmetrical ketone, suppose this is an unsymmetrical keto part which you have, which has two different types of alpha. In that case, you do two different parts here now. Notice, first is make two different enolate ions. Okay. Notice which enolate ion is stable. If you see the stability wise, this is less stable because double bond को stabilize करने वाले groups नहीं है, but here there are groups. Correct. So this intermediate is more stable. Does that make sense?
हाँ सर।
Okay. And if you compare, stability of the intermediate, sorry, this is enolate ion. But enolate ion, when you resonate it, which intermediate is appearing to be more stable? Because here we know that enolate ion is forming more in the form of this negative charge here, correct? So ये दोनों में से ज्यादा स्टेबल कौन सा है?
पहला वाला।
पहला वाला, right? This one is more stable. So बताओ, if at all I take a base from here, if I take a base from here and here and here, ये अगर R1 है, ये अगर R2 है, correct? Which kind of carb anion will form faster? पहला वाला fast बनेगा ना? So that means
हाँ।
R2 will be greater than R1, correct?
यस।
So fast, I mean, if you see the reaction wise, then this will become faster, which means this is a kinetically driven reaction or kinetically favored direction.
तो पर फोर्थ लिस्ट में हमने देखा ना कि अल्फा ज्यादा वो डबल बॉन्ड वाले पे आ रहा है, जो बीच में हुआ था।
ये इनॉल नहीं बना है, देखो ये इंटरमीडिएट नहीं है हमारे लिए, ये इनॉल कंप्लीटली नहीं बना है ना, ये वाला। इनॉल बनता है तो आप डबल बॉन्ड को कंपेयर करोगे।
ठीक है।
ठीक है बेटा, राइट। सो नाउ नोटिस दैट this one is at low temperature, sorry, this one is a kinetically favored one, this one is a thermodynamically favored one. Why thermodynamically favored? Because final product जब बनेगा enol, so in that enol form this one being more stable, correct? Now notice, I'll show you with the product as well. Done. Okay, so check out, this one is a fast step, this one is a slow step. Now of course this can be favored at low temperature, right? Because
हाँ।
kinetic is always, kinetically favored products are always favored at low temperature. Then the other one has to be at high temperature. Then this would be favored by bulky bases. Yes or no? Because you have learned this in uh, Hoffman eliminations, right? So wherever we have E2 with Hoffman, we always notice that uh, bulky bases will always affect on the position where there is less substitution. So if this carbon is less substitution, right, removing H plus from here becomes more easy for bulky base. So if you have a tert butoxide LDA, this will always take out H plus from this position, correct? So two cases you need to notice. One, low temperature. Second one, whether it is bulky bases. These two will always favor kinetically favored positions. Got it? Second, if you have a small basis and if you are favoring at high temperature, then definitely this type of carb anion is more favorable. Let me show you with a practical example. Practically, if this is an unsymmetrical ketone and you react with LDA, okay, LDA is a bulky base like this, okay, this one is LDA, okay, diisopropyl lithium diisopropyl amine, okay.
हाँ सर।
So this is a bulky base. So bulky base would usually go to extract H plus from here, and that is supported by low temperature also. And from there CH3 will be substituted. This is a product you will get, major product. But if you are treating with KH is H minus. H minus is a very strong base, but because it is a smaller base, it will take H plus from here, and you get negative charge here, correct? And that negative charge will attack on CH3, remove Br, and you will get CH3 substituted. So what do we get? This is thermodynamically favored product,
यस सर।
right, beta? So this is what you need to notice. Check out. If you have NaH, obviously this hydrogen is very acidic, okay, and bulkiness is not a problem here. So H minus will take H plus from here, gets a negative charge. That negative charge will attack here because SN2 is favorable here. So chlorine will be relieved. You will get this product. Okay. ETO minus. This was asked in JEE 2020 direct advanced question. ETO minus can take H plus from here. You get negative charge. That negative charge via SN2 mechanism will be able to attack on this position, remove bromine from here. Correct. And after bromine is removed, you will get this first product here. And then hydrolysis is done. Notice, if you have a keto group, sorry, ester group, on hydrolysis it will become an acid. And this acid is basically beta keto acid, right? And beta keto acids on heating, this will undergo decarboxylation. So this COH will go away. So remove that COOH. What is left? 1, 2, 3, 4, 5, 6. 6 carbon group is left. So this is the keto form you will get, and CO2 will come out. Okay. If you want to just recall how the decarboxylation happens, check this out, how it happens. We have discussed this during the preparation also, but notice this, how it is happening. Yes, any doubt here?
नो सर समझा।
Right.
सर
See,
पर
these
वो
are back.
इधर एक्टिव मिथिल ग्रुप है बीच में, तो वैसे भी H प्लस वो बीच में से ही निकल आया था ना।
निकलेगा बराबर, प्लस वहीं से निकलेगा।
हाँ सर।
देखो, दिस इज बैक टू बैक जेई क्वेश्चंस है, बैक टू बैक जेई क्वेश्चंस में आए, बैक टू बैक ये 21 में आया था, दैट इफ यू हैव ETO माइनस यू कैन टेक H प्लस फ्रॉम हियर। एक्सेस दिया है इस बार, एक्सेस दिया है तो पहला एक HCH3 होगा, फिर ETO माइनस फिर से रिएक्ट करेंगे, फिर से H प्लस निकालोगे, फिर से C माइनस आएगा, फिर से C माइनस अटैक करेगा, 2 times you will get methyl groups here, and thereafter again you are hydrolyzing it, you are heating it, so first you will get acid, and after the decarboxylation, and this is a final product you will report. Okay, clear beta?
हाँ सर।
Right. Now if at all you use LDA here, LDA will try to take H plus from here, and from here the internal attack will take place, removing this bromine, you'll get a 6-membered ring. But if it is NaH, H minus will take H plus from here, because this side is a more favorable thermodynamic case. From there it will attack here, Br minus will go, and this is the product you will get. Clear?
सर अभी वो NaH है सर, उसने भी 6 मेंबर रिंग बनाया, तो वो ज्यादा स्टेबल होगा ना फाइनली।
हाँ बेटा, देखो, but like I said, the reaction would be favorable based on where is that enolate ion with a double bond being more stabilized. Okay,
हम्म।
thermodynamically that's what we'll say. Thermodynamically what we will say, intermediate तो बना है, but in that intermediate where is that double bond coming out to be more stable form. Okay, now of course you may judge based on the stability of ketone. Stability of ketone suggests कि ये ज़्यादा stable है, isn't
हाँ।
it, compared to this one, isn't it?
यस।
Clear? But if you notice, this is an open ketone, so ये बहुत debatable हो गया. There are 3 hydrogens here, 1 hydrogen here, which is supporting, correct? So ऐसा stability को decide करना मुश्किल हो जाएगा. Understood? That's why you always go with that mindset कि यहाँ पे double bond किस तरफ ज्यादा stabilize हो रहा है. Go towards that as the thermodynamic product. Okay,
हम्म। ठीक है सर।
right. Next is alpha nitrosation. Alpha nitrosation is a very similar case. If you have, NaNO2 and HCl will make an electrophile NO plus. You make a pi bond first, right? Because it is in an acidic medium, you have to make an enol. Instead of ketone, you'll make an enol. Then from the enol part, the pi bond will attack on NO. You'll get N double bond O. N double bond O can be also represented as oxime, oxime by oxime tautomerism. So this is a final product you will showcase. Okay, clear? Oximes here are more stable because of the, conjugation like this, extended conjugation. Okay, yes, clear? Yes, any doubt here? You're on mute, beta.
सर ऑक्साइम इज मोर स्टेबल देन नाइट्रोस वाला है ना।
Yes, beta, due to extended conjugation, the lone pair will go here, pi bond will go here, pi bond will come here. Okay.
ठीक है सर।
Next, addition of alpha beta unsaturation here. See, now you have a double bond, then you have an negative charge coming here. In that case, this negative charge will push electrons here, gets a negative charge, and since this side the negative charge is more stable, the attack always happens from this end more often. So from this end it will attack, pi bond will shift, O minus will take H plus, and after attacking this is a product you will get.
तो
So
मेजर प्रोडक्ट सेकंड वाला
major
होगा।
product wise, this one is a major product. Clear?
हाँ सर ठीक है।
क्लियर बेटा? राइट, सॉरी ये नहीं, सेकंड वाला।
सेकंड वाला है ना? हाँ।
सेकंड वाला मेजर प्रोडक्ट। नेक्स्ट, सेम लॉजिक हियर आल्सो, इफ इट अटैक्स फ्रॉम दिस एंड, राइट? नो नो, मैंने दे दिया मेजर प्रोडक्ट कौन सा है। नेक्स्ट, चेक आउट दिस वन। नाउ इफ यू हैव HY टू बी एडेड, मतलब एसिडिक मीडियम में यू आर एडिंग, but this time the double bond is on this position here. Okay,
हाँ।
if the double bond is on this position now, so then what would happen? The lone pair will take H plus from here. Okay.
यस, तो ऊपर शिफ्ट होगा वो डबल बॉन्ड।
Hmm. Hmm. So H plus, and then Y can add here. If it addition is happening here, then that is called 1-2 addition, and 1-2
हम्म।
addition is typically kinetically favored product. Okay, but if at all we take, if at all we take this one, which is 1-4 addition, yeah. See, sorry, this one was something bad that came here. Let's delete it out.
सर पर काइनेटिकली फेवर्ड प्रोडक्ट क्यों होगा? वन टू
बता रहा हूँ,
एडिशन।
बता रहा हूँ, बता रहा हूँ. Okay. Now this one is kinetically favored. If the same thing happens at 1-4, that is called thermodynamically favored product. Okay. If you are making any 1-4 addition ना, तो सारे 1-4 additions का नाम होता है माइकल्स एडिशन. बस ये याद करना पहले. ओके.
हाँ सर।
1-4 एडिशन इज माइकल्स एडिशन. अब देखो मैकेनिज्म को देख के समझते हैं एक बार. ठीक है. 1-4 कैसे हो रहा है, पहले 1-4 समझते हैं फिर 1-2 पे आते हैं.
यस।
Lone pair is taking H plus from here. ठीक है. Then if the double bond is pushed here to make this oxygen stable, then at this position you will have carbon plus, which can be attacked by Y minus. So you will get this enol form, which will convert into a keto form. So this is 1,4 addition. Now in this 1,4 addition, if you notice what's happening, when the oxygen takes H plus from here, immediately resonance will drive it, because of which here the sigma, the pi star orbital which is present will experience, very low amount of energy. करेक्ट, यहां पर लो एनर्जी आ जाएगा. करेक्ट, बिकॉज ये पाई बॉन्ड इधर शिफ्ट हो गया ना बेटा. ओके. सो उसके पास इलेक्ट्रॉन डेंसिटी है नहीं जब तक. सी, रिमेंबर दिस वन, पाई एंड पाई स्टार में एनर्जी, अगर पाई बॉन्ड ज्यादा है, ठीक है, पाई बॉन्ड इज ट्राइंग टू ब्रिंग स्टेबिलिटी. करेक्ट. सो पाई स्टार में एनर्जी कम होगा.
हम्म।
सॉरी, दिस वे, सपोज इफ यू हैव C double bond C, then CH double bond C. Let's say like this. Okay. You have, this is a pi bond and this is a pi star bond. ठीक है बेटा. This is pi star and this is pi. Correct. If the
हाँ
bond is stronger here, stronger bond means less energy, right? So pi में bond कम रहेगा, pi
सर,
star में
स्ट्रॉन्गर
energy
बॉन्ड
ज्यादा
मतलब
रहेगा.
लेसर एनर्जी कैसे सर? स्ट्रॉन्गर बॉन्ड
स्टेबल हो रहा
मतलब
ना,
हायर।
बॉन्ड स्टेबल ना बेटा, बॉन्ड स्टेबल.
अच्छा।
मॉलिक्यूल लेस एनर्जी में रहेगा ना, स्टेबल
अच्छा
हो रहा है
पर
बॉन्ड.
फिर उसको तोड़ने में ज्यादा एनर्जी लगेगी ना?
हाँ बेटा, इसका मतलब वो
हाँ।
स्टेबल है ना.
यस सर। हाँ।
करेक्ट. तो उसमें ज्यादा एनर्जी लग रहा है, मतलब वो स्टेबल है, उसके पास लेस एनर्जी है. करेक्ट.
यस।
ऑर्बिटॉल्स के पास, मैं बता रहा हूँ, ऑर्बिटॉल्स के पास लेस एनर्जी है. करेक्ट.
राइट सर। हाँ।
तो पाई स्टार के पास क्या है, ज्यादा एनर्जी है. बराबर.
हाँ।
पाई स्टार के पास ज्यादा एनर्जी रहेगा. करेक्ट. अगर ये पाई बॉन्ड इधर शिफ्ट हो जाता है, तो अब पाई स्टार के पास कम एनर्जी रहेगा, राइट?
सर क्योंकि पाई के पास हाई एनर्जी आ गई इसीलिए।
यस.
हाँ।
इसका मतलब यहां पर कम एनर्जी का मतलब क्या है, कि इसके पास पाई कैरेक्टर बढ़ जाएगा. समझ गया? पाई
हाँ।
स्टार के पास पाई कैरेक्टर बढ़ जाएगा. ये
यस।
लॉजिक क्लियर है? ओके.
हाँ।
पाई स्टार का एनर्जी कम होना इज सेम एज सेइंग कि पाई का कैरेक्टर बढ़ रहा है उसमें. ओके. और क्योंकि पाई का कैरेक्टर बढ़ रहा है, कोई इनकमिंग न्यूक्लियोफाइल है वो इसको इनवाइट कर लेगा, इनकमिंग न्यूक्लियोफाइल को इनवाइट करेगा. ओके. इज दिस मेकिंग सेंस?
यस सर। यस सर।
राइट. So any incoming nucleophile will be invited at this fourth position more than the second position. Second position पे क्यों? देखो अभी ये पाई स्टार का ऑर्बिटल को ये पाई बॉन्ड कंफर्टेबली सपोर्ट कर रहा है, सो पाई स्टार का एनर्जी बढ़ रहा है ना,
हाँ
तो यहाँ पे पाई स्टार का एनर्जी बढ़ रहा है, यहाँ पे पाई स्टार का एनर्जी कम हो रहा है, तो यहाँ पे ज्यादा इन्वाइट होगा।
सर, वहां पे
करेक्ट?
भी 5 स्टार का एनर्जी बढ़ेगा ना, तो
नहीं,
फिर
ये पाई
वो।
बॉन्ड इधर शिफ्ट हुआ ना बेटा,
हाँ
तो
हाँ
ये पहले पाई था अभी पाई था, ऑलमोस्ट कॉम्पोजिट ही हो गया ना।
हाँ हाँ, वो ठीक है सर, पीछे वाला बोल रहा हूँ मैं, फोर्थ पोजीशन वाला।
फोर्थ पोजीशन पे यहाँ पे पाई स्टार का एनर्जी कम हुआ है, मतलब पाई का कैरेक्टर बढ़ रहा है,
हाँ ठीक है।
इसके लिए वाई माइनस इधर अटैक कर रहा है। लॉजिक क्लियर है?
यस।
राइट, अब देखो, since this is attacking here and this pi is going, now can you notice this pi which is forming, the enol which is formed is supported by sufficient amount of stability also by hyperconjugation. This is getting stabilized also, correct?
यस सर।
That is why this is thermodynamically favorable direction. अब काइनेटिक पे आते हैं। ओके, नोटिस, if at all you are preparing something like HCl, if you are putting like an HCl, HCN first lone pair has taken H plus. Now Cn minus has to attack either this side or this side. Is that clear? Okay.
हाँ
If Cn minus is going attacking on the fourth position, then I will say it is a thermodynamically favored product. Okay. But if you notice this carbon, right? If the temperature is maintained very low, the resonance nature will be less. So this carbon still possess sufficient positive charge. So what would happen? Initially positive charge कहां पर ज्यादा दिखेगा? इधर या इधर? इधर ज्यादा दिखेगा ना?
हाँ हाँ
सो इनिशियल पोजीशन पे जब पॉजिटिव चार्ज मिलेगा वहीं पे अटैक कर देगा, बिकॉज यू आर टू गो टू दैट डायरेक्शन वेयर द एनर्जी बैरियर इज लेस। करेक्ट?
हाँ। यस सर।
तो यहाँ पे जाने के लिए एनर्जी बैरियर ज्यादा लग रहा है, यहाँ पे जाने के लिए एनर्जी बैरियर कम लग रहा है, टेम्परेचर क्योंकि कम है। हम्म?
हम्म।
तो कौन सा डायरेक्शन सी एन माइनस विल चूज? दिस डायरेक्शन इट विल चूज। दैट्स व्हाई यू विल गेट KFP as a major product instead of TFP. But the minute you put it at a higher temperature, now suddenly it will become TFP product. Got it?
हाँ सर।
Hmm. So this is about 1,2 and 1,4 addition. Clear?
हम्म।
Right. Now notice it. At a normal temperature, except RMGX and RLI, most of the nucleophile will undergo conjugated addition product. Why? Because RMGX and RLI will have very strong basic nature. R minus is a very strong base. If temperature is not provided in any of these cases, if temperature is not given, and if the nucleophile is strong, strong nucleophile will always try to address the strong positive charge carbon, which is on second position.
हाँ
That's why the attack would always happen at 1, 2. इस case में भी 1, 2. इस case में भी 1, 2. But the minute you add RMGX with some copper salts, now it will become R2Cu, right? Mg. This is how it will happen. Correct? A
हाँ
complex will form. Now, if R is connected with copper, its negative charge decreases drastically. So it is not a very strong nucleophile. Okay. So since it
हाँ
is not a strong nucleophile, it will notice for a carbon which is trying to have more pi character. So which is at this fourth position. So therefore, if you have any copper salt, cadmium salts, right, or complexes forming, they all will go for 1,4 addition. Clear?
हाँ सर।
Any doubt?
नो सर।
So this is a very important area. 1,2 addition and 1,4 addition किस केस में करना चाहिए? Okay. Right. Now let's come to the condensation reactions. All condensation type of reactions, starting with aldol. Aldol is about taking an aldehyde or a ketone and adding with an alcohol. That will make it into beta hydroxy aldehydes or a ketones. That is called aldol. See, here beta hydroxy ketone, beta hydroxy ketone. beta hydroxy ketone. So these are all aldols. Okay. Now, aldol reactions can happen between two aldehydes, between two ketones, between aldehyde and ketone. Okay. What is the condition that will happen? What is the condition that is required? It must have at least one alpha hydrogen. Condition is every aldehyde or ketone which we are dealing with should have at least one alpha hydrogen. The medium has to be acidic, but basic is more favorable. I mean, both acidic and basic can be used, but basic is more favorable. The typical step in the aldol will be tautomerism step, enolate ion formation, nucleophilic addition, aldol formation, and lastly condensation. These are typical steps observed.
हाँ सर.
Okay. See, if you take an aldehyde in the presence of OH minus, first you'll get an enolate ion. This is the enolate ion formation. So there is a tautomerism enolate ion happening. So this is A and B steps. Okay. Basically, A is not a step, A is just a phenomena. I'm just trying to show that this phenomena with the enolate ion is happening. Okay. And then nucleophilic addition will happen. And because this enolate ion will have sufficient delta negative charge also on carbon, it can act like a nucleophile added to the second molecule. And as it adds to the second molecule, O minus will come. And wherever there is a nucleophilic addition, we have always learned that it is going to be more. Uh, you'll notice that it has to be more. Sorry, it has to be the rate determining step. So this nucleophilic addition will push this double bond to O minus, and this is what you'll get as the addition. Then O minus will take H plus from the water, convert that into aldol. Okay, this is the aldol formation. And what is aldol condensation? Once you get an aldol here, if you facilitate that by heating, you will get this OH and H being removed out, and that will convert into an alpha beta unsaturation. Usually, if you're carrying this in, water or OH minus, it will go via even CB mechanism. You can see if you take water, water will take H plus away from here, gets a negative charge. Why this negative charge is forming beta? Because negative charge can be resonance stabilized, and you know that if at the beta position there is a negative charge getting resonance stabilized, it will always follow even CB mechanism. So that negative charge will push here, OH minus will go, and you will get this alpha beta unsaturated aldehydes. And this is called as aldol condensated product. Clear with the mechanism? You're on mute.
सर सर aldol मतलब अल्कोहल जैसे ज्यादा करता है कि aldehyde जैसे.
Aldol is beta hydroxy aldehyde. Okay.
हाँ सर वो समझा.
कंडेंसेटेड प्रोडक्ट मतलब उसमें से वाटर हटा देंगे तो वो कंडेंसेटेड प्रोडक्ट हो गया. पॉइंट क्या है ना यश, ये सारे रिएक्शंस है ना हाईली रिवर्सिबल है. मतलब
हम्म.
अगर ये प्रोडक्ट बना भी ना, ठीक है, आपको OH माइनस रहेगा सॉल्यूशन में, इमीडिएटली H प्लस को हटाएगा, पुश करेगा वापस ये पुश करेगा, ये ग्रुप को निकाल देगा वापस ये. ठीक है. आपको पता है कितना परसेंटेज ऑफ aldol बनता है एट अ टाइम? हार्डली 1 to 2%.
सर
करेक्ट.
वो रिवर्सिबल होने से रोकते कैसे हम?
हाँ. अब रोकने के लिए ही दो प्रोसेस है. एक है जैसे ही एल्डोल बन रहा है उसको हीट कर दो ताकि वो अल्फा बीटा अनसैचुरेशन एल्डिहाइड में कन्वर्ट हो जाए. ओके. इससे ये रिएक्शन लेस बैकवर्ड जाएगा. दैट इज द फर्स्ट थिंग. सेकेंड थिंग, जैसे ही आपके पास अल्फा बीटा अनसैचुरेशन बढ़ रहा है, ओके, एक 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 पर्टिकुलर टूल, एक इंस्ट्रूमेंट है, ओके, जिसमें से इसको ही सिर्फ इसको डिस्टिलेट करने का प्रोसेस है वो. ओके. सॉक्सलेट एपरेटर्स कहते हैं उसको. इन दैट एपरेटर्स इट्स वेरी इजी टू distillate this part of aldol. Okay. So इससे रिएक्शन फॉरवर्ड डायरेक्शन में आएगा. एट एनी पॉइंट ऑफ टाइम आपको 1 to 2% से ज्यादा एल्डोल नहीं बनेगा. सो दीज आर एक्सट्रीमली बैकवर्ड रिएक्शन. करेक्ट. क्लियर बेटा?
Yes, sir.
Right. So in a base catalyst mechanism, mainly we saw three mechanism steps. One is carbanion formation, which is enolate ion, nucleophilic addition, and lastly even Cp mechanized to give condensed aldehyde. Okay. Now base catalyst mechanism, if you notice, this is what you got. This is the step which is made, and once you get an aldol, the third step what we learned it already. Okay. अब notice these cases to understand more about the mechanism. The first step is not the RDS. We can use anhydrous conditions to avoid the reversible step. Why? Because you are taking H2O out of this, and if you keep it in an aqueous solution, ये reaction mostly backward चला जाएगा.
हाँ
Yes or
सर,
no?
इसीलिए
So
H2O
that's why.
निकालते। हाँ
Yes, it's इसीलिए हम लोग काफी बार anhydrous बेरियम हाइड्रोक्साइड लेते हैं, पाउडर्ड फॉर्म में लेते हैं, है ना, ताकि रिएक्शन ज्यादा फॉरवर्ड जाए.
हाँ
ओके.
सर।
Second step. Second thing. Second step lies mostly in the backward direction. Hence, increase the enolate content to increase the production. ये कंटेंट मुझे बढ़ाना चाहिए, बट ये कंटेंट फर्स्ट स्टेप पे डिपेंडेंट है. मतलब इन अ वे ये दोनों एक ही स्टेप के बारे में बात कर रहे हैं. दैट ट्राई टू पुश मोर एनहाइड्रस कंडीशंस. ओके. थर्ड, removing product would help the reaction favored in the forward direction. So like I said, you use oxalate apparatus so that there is a continuous distillation which will help the reaction to go in the forward direction. Okay. So you can see barium hydroxide powder or hot acetone will help in a better condition. Clear?
हाँ सर। यस।
Next. If you go for an acid catalyzed mechanism, see, when it comes to base catalyzed mechanism, aldehydes के लिए तो बहुत अच्छा काम करता है, कीटोन्स के लिए बहुत बेकार है. बेस कैटलाइज मैकेनिज्म है ना. बेस कैटलाइज कब कब ठीक ठाक होता है, जब पाउडर्ड बेरियम हाइड्रोक्साइड लेते हो. एक्व सॉल्यूशन में तो क्वेश्चन ही नहीं है, कीटोन अनसक्सेसफुल है. ठीक है. एक्व सॉल्यूशन में कीटोन हमेशा अनसक्सेसफुल है टुवर्ड्स एल्डोल. ठीक है. ये बात ध्यान से रखना.
हाँ सर।
क्लियर. बट अगर मुझे एसिड कैटलाइज करना पड़े तो आल्डिहाइड से ज्यादा बेटर है कीटोन्स के लिए. कीटोन्स में एसिड कैटलाइज मैकेनिज्म ज्यादा बेहतर होता है. लेट अस अंडरस्टैंड व्हाई. सी, if I take 2 moles of this ketone and I react that in H plus, first you'll get an enol form. ठीक है. And from this enol form, imagine this pi getting attached on the second molecule because यहाँ पर obviously OH plus रहेगा. So this will go away and you will get this beta hydroxy ketone. Okay. To avoid the reversible reaction, first step has to be taken with dry HCl. So again, I can avoid aqueous solution, put dry HCl into it. Correct. After that, important logic is because the OH is coming at the third degree position, it can take H plus from dry HCl, converts into OH2, which is a very easy leaving group. So easily it can form carbocation. Then water can remove H plus from here, makes an enol form, which is very stable also, which is a keto alkene form, which is very stable also, right?
हाँ
So here overall process is exothermic, clear, and it is aldol plus dehydration which is happening. Got it? So
यस।
that's why this reaction is more favored in acidic medium. The product what you will get on one side is called, one side we will get a double bond that is called mesitylene oxide. But if I take the same mesitylene oxide with 3 moles instead of 2 moles, if I take 3 moles, this side also the same double bond can form. Hence, double bond now can form on both sides. That is called 4-one. 2 moles लोगे तो mesitylene, 3 moles लोगे तो 4-one. If the same 3 moles are been done in concentrated H2SO4, then that is going to form mesitylene. Okay, this is mesetyl oxide, 4-one and mesitylene. Got it?
फिर
Basically,
कॉन्ग फोर में फर्क क्या पड़ा?
Kong H2SO4 में mechanism का थोड़ा सा फर्क है. Let me show you the mechanism. Okay, आप समझो ये तीनों इनॉल बन रहे हैं, मैंने तीनों को इनॉल की तरह लिखा है। OH double bond like this, OH double bond like this, OH double bond like this, ओके। इनॉल लिखा मैंने। इमेजिन करो ये पाई बॉन्ड इधर अटैक कर रहा है, सॉरी माय मिस्टेक, वन सेकंड। कीटोन, कीटोन के फॉर्म में लिखता हूँ OH के साथ में, ऐसे। सो इससे एक्सप्लेन करना इजी होगा। OH प्लस ऐसा है, OH प्लस ऐसा है, OH प्लस ऐसा है, ठीक है बेटा, करेक्ट। नाउ
हाँ।
इन दिस केस imagine if from this end it will attack here, ओके। इनॉल के फॉर्म में अटैच हो रहा है यहाँ पर, और
हम्म।
ये इधर अटैक हो रहा है, और ये कार्बन इधर अटैक हो रहा है, ओके। सो
हाँ।
मेरे पास 6 मेंबर्ड रिंग ऐसे बनेंगे, जिसके पास OH ग्रुप आएगा, OH ग्रुप आएगा, OH ग्रुप आएगा, है ना।
हम्म।
हम्म। अब वंस दिस गेट फॉर्म्ड हियर, ठीक है, अब डिहाइड्रेट हो जाएगा, बिकॉज कॉन्सेंट्रेटेड H2SO4 में डिहाइड्रेट होके क्या बन जाएगा, बेंजीन रिंग बन जाएगा।
ठीक
डबल
है।
बॉन्ड डबल बॉन्ड डबल, ओके।
यस सर।
नेक्स्ट, व्हाट आर द टाइप्स ऑफ एल्डोल यू विल नोटिस। सी, फर्स्ट you would have this one here. You could notice that in aldol you have self kind, self aldol. When you have 2 moles of aldehyde, right, you can get this aldol. Now in this aldol you can notice that there are 2 chiral centers, so which means 4 stereo products you can get. After removing of water, that is condensation, you will get a double bond which will give cis and trans. There are 2 stereo products, right? So number of products agar question पूछा है, so you can get 4 stereo products of aldol and 2 stereo products of condensed aldol. Hmm? If you have this kind of aldehyde, so you'll get 2 stereo product of aldol, and further condensation is not possible because here there is no alpha hydrogen, so product will remain here only, okay. Next, if I take 2 moles of this one, you will get this particular aldol. यहाँ पे 2 chiral center है, correct, sorry, एक chiral center है, so that makes it 2 stereo product, and there is only one product, no cis and trans. If there is a ketone, you take solid barium hydroxide, so you'll get one chiral center here. On heating, you'll get a double bond which will have cis and trans product. All these examples are typically for self aldol. Hmm? Now
हाँ।
notice what is cross aldol. Cross aldol is if you have two dissimilar aldehydes and ketones. Let's say there are two aldehydes, one is propanol and one is uh, ethanol. Ethanol and propanol. In the presence of OH minus here, for this if you make a self, okay, देखो सेल्फ बनाने का शॉर्टकट क्या है, इसको ध्यान से देखना, सिर्फ CH3CHO को देखना, ओके। सो व्हाट आई विल डू, आई विल राइट दिस एज CH3C। जो एल्डिहाइड है उसको अल्कोहल बना दो पहले, ओके। जो भी एल्डिहाइड है उसको अल्कोहल बना दो पहले, बन गया, ठीक है।
हम्म।
अब बनाने के बाद सेकेंड मॉलिक्यूल, ये इसी को सेकेंड मॉलिक्यूल की तरह एज्यूम करो, और ये वाले कार्बन को इसके साथ अटैच कर दो, राइट। सो विच इज CH2, क्योंकि एक हाइड्रोजन चला जाएगा, CHO, डन। बस ये हो गया आपका सेल्फ एल्डोल, समझ गया।
हाँ।
तो हमेशा कोई भी मॉलिक्यूल है तो ये देखो CH3, CH2, first make this carbon into alcohol form, then attack the alpha carbon here, this is the alpha carbon, उसको अटैक कर दो, so CH, CHO, उसके साथ में एक CH3 भी है, done, this is the self aldol, correct. So
हाँ।
that's the way you can easily make self aldols, okay, here. So you can, I made first self aldol, then you make two cross aldols. One cross is this CH2 minus attacking here, one cross is this CH2 attacking on this carbon, okay. So you'll get
हाँ।
two cross, you'll get two self. In the self, you got one chiral center here, two chiral centers here. In the cross, you got two chiral center here and one chiral center here, which makes it how many total aldol products? This was a JE question. How many total products you can get? Answer is 12. अगर ये पूछा है aldol condensed product, answer is 8, because उसमें से भी you just need to make it into double bond. So we make one double bond here, double bond here, double bond here, and double bond here. All of them have cis and trans. So therefore we have 8 products here. Clear with the cross? This has come in recent JE only beta. So learn it thoroughly. So ऐसे questions आ सकते हैं. Okay. Next, intramolecular. Whenever there is an intramolecular, ring ability को check करना पहले. So you need to have 6 carbon, more than 5, then 7, then 4. This is the ring ability which you will get. Okay. So if you notice OH minus can be extracted H plus from here, and that minus can go attack here. So that makes it as a 4-membered ring, and this is the condensation product. If you have barium hydroxide and heat, now notice this carefully.
सर वो अंदर
From
वाले को
here,
क्यों किया सर, बाहर वाले को क्यों नहीं किया?
बाहर है ही नहीं ना बेटा, दिस इज aldehyde.
हाँ यस सर.
नेक्स्ट वाला एग्जांपल है कीटोन वाला, देखो. नेक्स्ट वन इज ए कीटोन एग्जांपल, बोथ साइड्स कीटोन आर सेम. सो कीटोन आप इधर से इधर अटैक करो या इधर से इधर अटैक करो, फर्क नहीं पड़ेगा, यू विल स्टिल गेट अ 6-membered ring. बट अब यहाँ पे देखो फर्क पड़ रहा है. One side is an aldehyde, one side is a ketone, correct? When there is an aldehyde and ketone, you know that aldehyde is always more reactive. So you need to, जहाँ पे more reactive उस तरफ alcohol बनाना जरूरी है. Okay? So this side you need to make an alcohol part. Okay?
यस
So
सर.
if you are making an alcohol part here, so attack can be done from 4th carbon or a 6th carbon. ठीक है? अब 4th carbon से करेंगे 1 2 3 4, तो आपको क्या मिलेगा?
4
4
मेंबर रिंग,
membered ring.
तो 6
यहाँ
से
से
करें.
6 membered ring. So कहाँ से करेंगे? 6 से करेंगे. ठीक है? So
हाँ
this will
सर.
be the more stable form. Now
सर हमने
notice here.
अल्कोहल कर दिया अल्डिहाइड को क्योंकि मतलब डेल प्लस उसका कम है इसीलिए ना, तब ज्यादा
Yes,
है.
del plus उसका ज्यादा है, aldehyde का ज्यादा है.
हाँ
Now here if you notice, from here if you make it, it is 5-membered ring. If I make it from here, it is 7-membered ring. So which is more favorable?
5.
5-membered. So this is the product you will get. Okay. Same logic here. From here, if at all I attack, it will be 6-membered ring. From here, if at all attack, it is 8-membered ring. So which is favorable? 6-membered.
हाँ
Within this ring, there is this is symmetrical. So कहीं से भी attack करो, one will be 5-membered, the other one will be 7-membered. Okay, okay. This
यस.
is the JE question. Check out. बहुत ही स्टैंडर्ड क्वेश्चन है, बहुत बार पूछ चुके हैं ये वाला JE क्वेश्चन. कि यहाँ पर डबल बॉन्ड है, you did ozonolysis, you will get aldehyde and aldehyde, right? So internally from this CH2 minus you can attack on this carbon, convert into this enol form. You make a if you heat you will get a double bond. This is the final product. Okay,
यस सर. हाँ
right. The next type of aldol is called Robinson annulation. Okay, Robinson annulation is a reaction where you first make a Michael's addition followed by aldol. Okay, for example, this is a keto group, this is a unsaturated alpha beta keto group. In that case, first what you do, you take OH minus, remove out this H plus from this keto group, you can get this negative charge, which will have a sufficient nucleophilic character to push on the 4th position. Double bond will be pushed here and O minus will come here. So here what you are doing, you are making a Michael's addition, right? Because it is a 1,4 addition. Once you get a 1,4 addition, in water, you take this H plus ion, you convert into an enol form. This enol will tautomerize to convert into keto form. Now once you get a ketone, now you have a ketone, which you have a diketone internally. So which means intra aldol is possible, correct?
हाँ
So now you have 1, 2, 3, 4, 5, 6. So from this end, the attack is possible. So as you attack, you will get this part, and on heating, you will get this product. So what is the product you will write here? The product you will write here is this one. The double bond. Oh, this is major product.
सर वो डबल बॉन्ड का पोजीशन वैसे क्यों आया सर, वो बीच में क्यों नहीं आया वैसा?
देखो बेटा, यहाँ पे एक्सटेंडेड कॉन्जुगेशन होता है, तो हमेशा ये वाला आपको इजीली निकल जाएगा. इवन सीबी मैकेनिज्म फेवरेबल.
ओके समझा.
ठीक है.
मेरे को लगा हाइपर कंजुगेशन।
ना ना, इवन सीबी आप सिर्फ याद रखना, इवन सीबी का पोजीशन बस।
हाँ
ओके, रॉबिन्सन एन्युलेशन वेरी इंपॉर्टेंट फॉर एडवांस्ड। ओके, so let me mark that, very very important for advanced exam. Okay, next, nitroaldol. Nitroaldol is, instead of having aldehyde or keto group, now you have nitro group. So nitro is a very strongly withdrawing group, so OH minus will always attack here first. So H plus निकालेगा, CH2 minus will form, it will attack here, and you'll get aldol, and on heating it you'll get cis and trans isomers. This is again a condensation. So instead of aldehyde being present here, aldehyde or ketone, now we have nitro group. That's why it is called nitroaldol. Same thing can be done with cyanoaldol. So CH2 minus will come, attacks here, you'll get aldol, then double bond, you'll get cyanoaldol. Okay.
सर, दिस और ट्रांसफर वो कैसे डिसाइड करेंगे नाइट्रो
हम्म,
एल्डोल में?
क्या
नाइट्रो
बेटा?
एल्डोल दिस या ट्रांस वो कैसे डिसाइड करेंगे?
स्टेबल इज मोर ट्रांस, यूजुअली ट्रांस ज्यादा स्टेबल, बट ये क्वेश्चंस कभी नहीं पूछेंगे जेई में, बिकॉज इन aldol डिसाइडिंग परसेंटेजेस इज वेरी डिफिकल्ट. ओके, यू विल
अच्छा
नेवर
ठीक।
बी आस्क्ड टू फिगर आउट विच इज मेजर, ट्रांस है या cis, ये कभी नहीं पूछेंगे आपको. ओके,
हाँ
नेक्स्ट, नो विनिगल रिएक्शन. No vinegar reaction is with an active methylene group. So, for example, I have CH2 connected with COOAT, COAT. In the presence of ETO minus, ETO minus is a strong base. It can take H plus from this active methylene, create C minus. That C minus can go attack carbon. You'll get this aldol form. Okay, and that on heating, OH and H can go, double bond will form. So this is a product you can get.
समझे।
Usually in JEE यहाँ से फिर से reactions आपको करवाएंगे, बोलेंगे कि फर्स्ट हाइड्रोलिसिस किया है यहाँ पर, सो व्हाट डू यू डू, विल मेक CH3 C डबल बॉन्ड विथ COOH एंड COOH. ओके, फॉलोड बाय हीटिंग बेटा. हीट फॉलो करने पर क्या होगा, डी कार्बोक्सिलेशन हो जाएगा, एंड you'll get this as CH COOH. what are you getting, cinnamic acid. सो ये एक स्टैंडर्ड रिएक्शन है सिनेमिक एसिड बनाने का.
तो हीटिंग करने पे वो CO2H पूरा कैसे उड़ गया?
ये ना, ये बीटा डाइएसिड है ना, बीटा डाइकीटोन की तरह बीटा डाइएसिड में भी CO2 चला जाएगा.
हाँ सर मतलब अगर
सेम
ऐसे
सेम
CO H CO2H
मैकेनिज्म, यहाँ
रहता।
पे देखो डबल बॉन्ड O, दिखा रहा हूँ मैकेनिज्म. H है, यहाँ पर डबल बॉन्ड O है, ये बीटा की बीटा एसिड्स. ओके, यही बीटा एसिड है ना बेटा,
हाँ राइट सर।
यहाँ पे OH है बस. हम्म,
हाँ
आप देखो यहाँ से ये पाई बॉन्ड इधर बॉन्ड बना रहा है, ये इधर टूट रहा है, ये इधर टूट रहा है, तो क्या बनेगा, OH डबल बॉन्ड OH. अब ये टॉटोमरेज होके वापस एसिड में कन्वर्ट हो जाएगा. क्लियर?
हम्म।
So wherever you have a beta diacids also, you convert into COOH on heating. Okay. Next, what is retroaldol? Retroaldol is reverse of aldol, and this will give you different route of aldol. Suppose there is already present an aldol here. Okay, you keep doing all the reverse reactions. So first, with dilute OH minus, attack on the position where the double bond can shift and O minus can form. So as the OH will add here, you'll get O minus here. Correct. This minus can take H plus. So what did we get? Originally, this was the aldol. So we got original aldol what it was. Okay. And this aldol came with an O minus charge. So पहले H plus हटा दो OH से. Then O minus will be pushed. This will become minus. So this is the enolate ion which was formed. And if I take H plus from here, this was the original aldol. Now you go to this mechanism. This is the exact way how we did aldol, right?
हाँ सर।
Now this is the one which we called as retroaldol. Now, once you get a retroaldol, that means you are back to the original aldol. This was the, sorry, back to the original keto group. Once you get a original keto group, from there, now you can make a different position reaction. Why? Because now you got this as the aldol, this as the keto group. This is a keto group. Earlier, OH minus took H plus from here and that attacked here. The other type of aldol is also possible, na beta? This OH minus can take H plus from here and this can attack here.
हाँ
So now this O minus can go attack here, and then you can get this alcohol OH and methyl here, and this OH and H from here can go and double bond can form. So this can be the other product. So that means if you keep this in basic medium, this will again get in equilibrium with this one. Understood? So these two will be in equilibrium. So retroaldol means from one aldol going towards the other aldol.
हाँ सर वो शॉर्टकट क्या था?
Shortcut कैसे है ना? When you are not able to figure out the entire mechanism to get back what was the original ketone, just break the double bond, give H on the C double bond O direction and OH on the other direction. So when you get OH here, correct, that OH you convert into keto form. That's it. And here you will convert this into CH3 form. Done?
हाँ यस सर.
Now same logic in the next question also. Here I broke it. This side I make it as H, which means CH3. This side I'll make it as ketone. And then from here I made an attack, and that will give you this one. OH and H can be removed, double bond can form here. So this is the final product.
सर अब अल्टरनेट क्यों बनाए थे हम? अभी तोड़ा है हमने जस्ट, तो फिर अल्टरनेट बनाने की जरूरत क्या है?
No, we are trying to show beta this aldol is as much possible as that of this aldol. Okay.
अच्छा.
So if this was your original reactant, ये थोड़ी कि सिर्फ यही प्रोडक्ट बनेगा, ये भी तो बनेगा ना.
राइट सर.
तो हम लोग ये बता रहे हैं कि अगर आप ये प्रोडक्ट दे रहे हो, इसका मतलब ये प्रोडक्ट भी पॉसिबल है. यही बताना रेट्रो एल्डोल है. ओके.
समझा.
नेक्स्ट, Perkins reaction. Perkins reaction is very similar to that of aldol. How does it happen? Let's see. Here you need to take an benzaldehyde, right? This is specifically for aromatic aldehydes, okay? With an acetic anhydride. So this is an acetic anhydride, okay? And this acetic anhydride, when you react with CH3CO minus, okay? So what would happen? The aldehydes, oxygen, and the two hydrogens from this carbon will dehydrate. Hmm? And the other side where we have an acetate group, that will come out as acid, because ये water और ये CH3C double bond हो, that will convert into water, and rest of the part will join with this one, convert into cinnamic acid. Okay, shortcut clear है? Yes, can we go ahead?
1 minute.
Hmm.
हाँ सर. सर इसका मैकेनिज्म कैसे रहता है?
चलो, let's see the mechanism. CH3CO minus is a base which can extract H plus from the alpha position of an anhydride. So you will get this as CH2 minus. Of course, this is sufficiently reversible as well. So CH2 minus COO, CO, CH3 बन रहा है. Now this will start attacking here, which is also reversible, but this will happen very slowly because the reactivity of benzaldehyde is very, the reactivity of benzaldehyde is very low for nucleophilic addition. So this CH2 minus will add, you will get this O minus. Now notice this O minus here. Once you have a O minus here, correct, you have this C double bond O internally. So this O minus can go attack on this C double bond O, creates another O minus here. So this way a cyclic structure can be formed. A 6-membered cycle. 1, 2, 3, 4, 5, 6. Correct? And once you get this O minus, that O minus can push here, break this bond here into COO minus. Okay. So in short, this entire C double bond O CH3 got added onto this oxygen. यहाँ पर आ चुका है. And this part will still remaining with that carbon, which is CH2CO minus. Okay. As that happens, CH3CO minus will attack on this H carbon, takes away this H plus. You get a negative charge. That negative charge will push into a double bond form, break this bond. because again this acetate is a good leaving group. As it pushes here, you get a double bond, C double bond O, O minus. And this bond was removed, CH3CO minus has come. And both on hydrolysis will convert into cinnamic acid and acetic acid. Clear? You're on mute.
Yes, sir. समझा.
Okay, right. So don't worry. I think the mechanism part, what was asked earlier, was this one. Is there a six-membered ring intermediate forming? Answer is yes. Okay.
हाँ.
Is there an acetate forming as an intermediate? Answer is yes. Okay.
हाँ
बस
सर.
इतना पूछा गया. इतना पार्ट आपको पता होना चाहिए. ओके.
यस सर.
नेक्स्ट.
सर अभी नेक्स्ट टाइम करना हो सकता है क्या?
या. ओके बेटा. once
हाँ
again.
सर.